Welcome to video 3 in the Marching Cubes and Minimal Surfaces series. This is the third and final lookup table video. After this we'll have a completed lookup table. In this video we're going to match our transformed meshes with their Boolean patterns, and then we will organize them into a mesh component that has one mesh per branch, and the branch paths themselves will be the associated Boolean patterns for each of the meshes. In this video, there are two Rhino 7 scripting components, two Rhino 7 C# components that, if you're using Rhino 8 or something maybe even newer than that, will be slightly different, but the code inside them is exactly the same. And so if, later in the tutorial, you'd like to come back and look to compare your code inside the Rhino 8 scripting component with this one here, this is what it would look like in the Rhino 8 scripting component. This is the first one we'll write. This is everything inside the run script function, and this is all of our custom additional code. And this is the second one we'll write. This one's even more straightforward. Everything's just exactly the same because everything is inside the run script function. So in the last video, we transformed, essentially rotated and mirrored our meshes in different ways. And we also applied the same transformations to our cube points, to the corners of our cube. Now that the cube points are in new positions, we would like to see what are those new positions and map them back to their original positions, where they started, so that we can grab the Boolean values from those starting positions and move them into the new slots, the slot that represents the corner's new position. This will give us a set of rearranged Boolean patterns, and since we transformed the meshes in the same way as the cube corners, these rearranged Boolean patterns corresponding to the transformed cube corners will also correspond to our meshes. So now we will write a script that tells us which new slot our transformed corner points are in. This is pretty straightforward. We just need to compare them to the original cube corners and see which one they're equal to, which of the original cube corners they share x, y, and z coordinates with. You might first try using an equality component for this, set our transformed cube corners to the original cube corners and see which ones are equal, but I found that this actually isn't reliable enough, so we're just going to write our own C# script. We're just going to take in these transformed points and we actually want them to be in their own branch. Right now we have 48 different branches, and that's because we have 48 different transformations. Let's get one branch, let's get 8 branches for each of these existing branches by grafting this. And so now each point has its own branch, and this will make sense once we're in the C# component. So let's make that component C#, and we'll call this input trans points. So this is going to be our tree of transformed points, and so let's get tree access and type hint point3d, and cube points, list access, and also point3d. So inside this component we're going to make a function here that checks to see whether or not point A is equal to point B. So let's get public function. It's going to return a Boolean. It's going to tell us yes or no, is this point equal? We'll call it is equal, and it's just going to take in two point3ds, so point3d A and point3d B. And so let's make that Boolean, we'll call it equal, and we'll set it to false to start, and then at the bottom we're going to return equal. And in the middle here we'll check to see whether or not these points are equal, so let's get 3 doubles x, y, and z for point A, so double ax equals a dot x, double bx equals b dot, double ay equals a dot y, and az is a dot z. And we'll copy this and do it for b. And then let's get a difference, and we're going to measure the difference between the x value of A and the x value of B, and the difference between the y's and the difference between the z's. And then we're going to add up all those differences, and we're going to put that into a variable called diff. So double diff equals, and we're going to use the absolute value because it doesn't matter when we're subtracting, if it's negative, we want everything to be positive. So we'll do math.abs, and I'm just going to copy this. And this is going to be ax minus bx. This will be ay minus by, and the z's will be in this last one. And so if this diff, need a parentheses here, so if the diff is less than 0.01 is a good tolerance. So if we set it to 0, it still might find enough differences between these rotated points and the original cube points that it won't call them equal. So we're just going to put this tolerance of 0.01. And so if it's this close, if all of these values are this close, then it's probably, almost certainly, it's the same point, or they have the same coordinates, and that's what we want to know. So then if diff is smaller than 0.01, then equal is equal to true. They are equal, and we'll return equal. And now we can go up top and check each point. And we're going to output a data tree of integers. And we can call this map indices. And it's a new data tree. So I'm just going to close this out to see if I made any mistakes yet. Okay, not yet. Okay, back in here. And this data tree is going to have the same structure as, I'm going to close this out, as this. So before we grafted this, remember, let's ungraft this. This had 48 different branches. And we want our data tree coming out of A to also have 48 different branches. So we're going to start with a for loop, int I equals 0, I, and it's going to be less than the transformation points, the branch count divided by 8. So get branch count and divide that by 8 because we grafted it and that gave us 8 times as many branches. So we're just going to divide that by 8 to get it back to 48 different branches. And then I++. And within this for loop, each time we want to make a new branch for our map indices tree. So let's get a GH path component, or let's make a GH path, and we'll call it PTH equals new. And these are going to have the value I, the number designation I each time. And so that will go from 0 to 48. And so these will be the branches for our map indices. And it still might be confusing, but we're almost there where this should make sense, or it might make sense. So next we're going to do another for loop within this. So j equals 0, int j. J is less than, and this time it's just going to be 8 because we need to do this 8 times for each of the 8 different points. So we're kind of adding back this divided by 8 here. So j is less than 8 and j++. And then immediately one more for loop. This is kind of a lot of for loops, but it's okay. So this one we'll call k. So int k equals 0. K is less than, and this time it's going to be also 8. And this for loop, we're going to be grabbing the points from the cube point list, and that's 8 long. So we could do, cube points dot count. We want to be a little more explicit about what this for loop is counting. And then k++. And then let's get our points to compare. Now that we're deep enough in here, we can grab a point from our transformation point tree. So trans points. So I'm going to copy this, and I'm going to say point 3D, and we'll call this point A. And it's equal to our transformation points, our trans points dot branch. So we need to get to the branch that is it's going to be designated by ij. So I was our original branch, one of the 48 different transformations, and then j is the actual point within that branch. So this is going to be, the branch is I, j, and then the point, since there's only one point in each of these branches now, is just 0 every time. So now we've gone to the end of each branch and grabbed a point, and now we're going to see, is point A equal to point B, which is going to be from our original cube point list. So let's make another point 3D, and this one's going to be called point B, and this is just cube points K. Then let's check to see if these points are equal. So if is equal, and we have point A and point B, then we're going to do something. We will, actually I don't need these, it's just one line. So if they're equal, then we're going to add to our tree this value k to this path. And so what this is going to give us, I need one more parentheses here. Okay, so if A is equal to B, then whatever index that within the cube points is, so this is 0, 1, 2, 3, 4, 5, 6, 7. So we just went down a branch and we found this new rotated point. Maybe it was 0 that rotated over to here. So now for our first transformation of 48, if we had 0 rotate to over here, this is still going to be our first point in the list. So our first point in the list of this transformation branch will have this index. It'll have 0, 1, 2, 3, 4. It'll have index 6. And so this is going to give us 48 different lists of integers. So it might be something like 6, 4, 3, 7, 1, 0, or something that's 8 integers long, right? That's going to point back to the original index position that they're in now, to that they've moved to. And so when we get this list coming out, I'll walk through that again because it's probably a little confusing. But for now, let's just see if this is working. And let's return A, which is going to be our map indices. And let's see if I made some mistakes. Yes. Oh, I wrote pointed instead of point 3D. Right here. Okay, so now let's see what's coming out of A. So this says it's 48 branches long. That's what we want. And so for instance, branch 0, which was our identity matrix transformation, it's telling us that the first point in this branch is equal to the first point in this cube point list. So index 0 is equal to 0, index 1 is equal to 1, index 2 is equal to 2, and so on. So that's good. That's a good way to check that this is probably working. In the first transformation, it's saying the first point in this list is right here. It's at index 1 of our original point list. And then the second point in that list is at 2, then 3, and then 0. So this just rotated 90 degrees around this way. So this is just a tree that is matching up, telling us where the points moved to. And so we can use this to move our Boolean list, to reorganize this Boolean patterns that we have coming out of here. So let's just grab this pattern list. I'm going to get an integer component, and I'll name it bool patterns. And I'll also hide the wire display. I don't think I grabbed this yet. So we just need to match these up. And the clearest way to do this might be just to explode this tree into its 14 different branches and then do each branch separately. So I'll delete this, and let's get a bang component, explode tree, and there are 14 branches, so we need to go to 13. So I'll click this plus until we get to 13. Okay, now it's good. And we also need a series component from 0 to 7 for our 8 different, so let's just do 8 for 8 different points. So that's a series from 0 to 7. And the reason we want this is because we're going to sort this list from that goes 0, 1, 2, 3 all the way to 7 based on what's coming out of this component. So let's get a sort list component. So this is the list that we want to sort, and these are the key values coming out of here. So let's get a panel again just so we can see again what's in here. So these are pointing back to the original indices. And so if we sort each of these branches, each of these lists according to, or if we sort this list, this 0 to 7 list according to each of these lists, then it will kind of reverse the way that these are pointing. So let's do that and see what's coming out. And I'm going to simplify this. or that's not the one I want. I'm going to simplify this one. So if we go to branch 1, we can see this is basically a mirror of this. So this was 0 pointing to 1. Now we have 1 pointing to 0. This is 3 pointing to 0. We have 0 pointing to 3. So these are going to be our list items for these Boolean patterns. So let's get a list item component. These are going to be the indexes. So we're just going to rearrange these Boolean patterns according to these lists here. So let's plug this into there, and we need 14 of these. So that's 3, 12. Let's delete these now. 2 more, I think. And so these are going to be our lists. This one is just 0, 1, 1, 1. If we go down here, this Boolean pattern is 0, 1, 0, 1, 1, 1, 0, 0. And so we're just going to reorganize these Boolean patterns according to each of these index lists, indices, list of indices. So let's grab one at random, just one of these lists. And if we scroll down to the bottom, we can see that we have 48 different lists now, and these are corresponding to the 48 different transformations. So just in this component, we have our mesh at branch 7 is being transformed 48 different times, and each time it's transformed, this is how the Boolean pattern changes. And so at transformation on branch 16, the Boolean pattern looks like this: 1, 1, 0, 0, 1, 1, 0, 0. And at transformation 17, it looks like this: 0, 1, 1, 0, 0, 1, 1, 0. So let's get all of these back into one component. We separated it because it's a lot easier to see what's going on when you do it this way, but it will be easier moving forward if these are all in one component, all of these Boolean patterns, all these Boolean pattern lists. So let's get an entwine component. And right now flatten inputs is checked, but we don't want to do that. We need to preserve the extra branches. So I'm going to uncheck flatten inputs, and then let's start plugging these back in, or plugging these in. Need a lot more. All the way to 13. Okay. Next, we need all of our transformed meshes. So we have our patterns. Now we need the actual meshes that were rotated and mirrored, and these are coming out of this output. So let's get a mesh component and put these meshes in here. Hide that. So we have our original 13 or 14 branches, 0 through 13 you see on the left, and then within each of these branches has 48 different meshes. So let's call this trans meshes. Just call it all because we're going to be rearranging these. So I'm going to hide this wire, bring it over here. And there's one more thing we haven't considered yet. Even with all of our rotations and different transformations, we haven't just flipped the Boolean values. So within all of these meshes and within all of these patterns, we still don't have, or we probably might not have, one that has a 1 here in all zeros instead of a 0 here in all ones. So we just need to quickly flip all of the meshes and flip all of these Boolean values. So flipping both of these is really easy. Let's get a not component. And so every time a 1 goes in here, a 0 is going to come out, and every time a 0 goes in here, a 1 is going to come out. And let's get a flip mesh component. I'm going to hide this, and these should all be true by default. So reverse faces, flip the normals, and flip vertex normals. So now these match up with these, and these match up with these. And next we'll make a C# component that organizes all of these meshes based on the Boolean patterns. So to find which mesh we want, we're going to follow a path that is the Boolean pattern. So for example, this one would be branch 0, 1, 1, 1, 1, 1, 1, 1, 1, or just 0 with 1 sevens. So that's the branch path. So that's going to be a quick way to locate which mesh we want. So let's organize that with a C# component next. This C# component is going to make a tree of meshes, and the branch paths are going to be our Boolean patterns. So I'm going to get a C# component, and there will be 4 inputs because we have 4 different trees here. We'll call this meshes. This one can be patterns. And then we have negative meshes and negative patterns. So this is going to be a tree axis, and it takes in the type hint is mesh. This is also tree axis, type hint, mesh. This will be tree axis with type hint integer. And this is also type hint integer and tree axis. Just checking these. Okay, those should be good. So these are our original meshes, and these are the original Boolean patterns. These are our flipped meshes, what we're calling negative meshes, and these are the negative, the inverse Boolean values. So inside the component, this is pretty straightforward. Our output is going to be a data tree of meshes, and we'll just call this all meshes equals new data tree. And then since we won't have meshes for the 2 null cases where these are all zeros or these are all ones, we'll need to construct those paths manually. For the rest of the paths, they'll be constructed as we run through all the incoming meshes and all the incoming patterns. But the 2 null paths we need to make ourselves. So let's get a new GH path, and we'll call this one zeros equals new GH. And this is just 8 zeros. So 1, 2, 3, 4, 5, 6, 7, 8. Whoops. One more. And then the next one is going to be ones. We have 8. And then for all meshes, we need to ensure these 2 paths exist. So let's go all meshes dot ensure path zeros, and then copy this, and we'll put ones here. So that way we have paths for the null scenarios where they're all ones or all zeros, but we just won't put any meshes in those at the end of those paths. So next, let's do a for loop across all the branches of our incoming meshes. So for int I equals 0, I is less than meshes dot branch count. And then we'll go through another for loop for int j, and this will be along each of the meshes at the end for each branch. So int j equals 0, j is less than meshes.branch I. So for each branch, we're going to count how many meshes are in that branch. So dot count, and then j plus plus. So we're going to each mesh in this tree, and then our brackets, and then within for each of the meshes in this tree, we need to find what the associated pattern is, and these are organized in the pattern tree. And the way we've set up our pattern tree is each branch is designated with 2 integers, and these integers are going to be equal to I and j. So each time we get to a new mesh, we're going to make a new GH path, and that GH path is going to be whatever the Boolean pattern is at ij, at branch ij. So GH path, we'll just call it PTH, equals new GH path, and here we will put the Boolean pattern list that's at the end of this branch. So let's get patterns dot branch ij, I comma j, and then the first integer in that list is going to be the first integer in this new tree branch path, and so on. So we're going to have every path is going to have 8 integers, and those 8 integers are going to be the 8 integers from our Boolean pattern. So let's copy this 8 times. So how many is that? That is 7. One more. And this is going to be 1, 2, 3, 4, 5, 6, and 7. So remember, each Boolean pattern is 8 integers long, so we have 0 through 7. And each Boolean pattern can be used to describe a branch path to one mesh. And because of the way that we organized everything coming in, this list of Boolean integers, 1s and 0s, corresponds to mesh branch I index j. So let's get mesh branch I index j and put it in this all meshes data tree. So let's make a new mesh first. So new mesh, and let's set this mesh equal to branch I index j. Then let's add this mesh to the tree. Let's grab this first. So all meshes dot add, and we're going to add this mesh at this path. And that's all we need to do. But we need to do it twice because we have all of our positive meshes and patterns and all of our negative meshes and patterns. So I'm just going to copy this whole thing, and we'll do it again, but this time with in meshes instead of meshes. So every time I see in meshes or meshes, I'm just going to put in meshes. So down here, and every time I see patterns, I'm going to replace it with in patterns. And I think that will work. I'm going to put A equal to all meshes, and hopefully I didn't make any mistakes. Okay, let's hide this output. Now let's get a number slider. Well, first let's just get a list item, because all of these branches will have multiple meshes in them, and those will be duplicates. They'll be the same. So list item. So let's just grab the first item from, hide this first. First item in every branch. And now to check to see if this actually works, let's get our little display set over here. So we have all of this. I'm just going to copy all of this. And we don't need this, so I'm going to disconnect this. Don't need this. This is going to be, I'm going to disconnect this. But this will be our tree. And to get a path, I'm going to get a slider between 0 and 1. Duplicate it 8 times. Merge all of these values. And this is going to be our pattern. So I'll just call this the pattern. And so this can go into where we had the pattern going in before, into the index. I'm going to hide all of these actually. Do I need these again? I don't know. I'm going to bring it back over here. Oh, I have them. Okay. And this pattern is also going to go into here for our path. So hide this wire, bring this here, and just so we don't have that long wire paint. Okay. So at all zeros, this is just an open space. There's no mesh. Let's see if we put 1 there, then the arrow is pointing towards the sky, essentially, these blue dots. And so any combination of this is going to give us a different mesh. And so far, they look like they're working. I'm actually going to show that again. Makes it a little clearer. Okay, so these look pretty good. Just to be sure, let's make sure we actually have 256 in here. And I'm hovering over, and it does say 256 locally defined values. So we do have 256 meshes, or at least 256 branches. The all zeros and all ones are nulls, but they're counted in that total. And so that's good. So what's coming out of here is actually all we need for the marching cube algorithm. These are all of the possible meshes. So right now, just to be sure, I'm going to grab a mesh component, put this in here, hide it, and we'll just call this all meshes. And this is kind of the fruit of our labor. This is what we've been working for. And so we should internalize this data. This is going to be important for us later. Now we're done with the lookup table, so we can jump right into the marching cubes algorithm itself, and this will be our most important input for that. In our next video, we'll bring back in periodic minimal surfaces. We'll start visualizing them in different ways and set up the conditions so we can finish the marching cube algorithm with them. It's going to be great. See you there.